Thanks once again for joining. We had a wonderful session yesterday. We had keynote sessions as well as a moderated panel in the evening. Today we're going to have a couple of panel sessions and tomorrow as well 2 more. So I hope we are changing gears a bit into more technical conversations today and tomorrow. I invite the first moderator today and with him to invite the panelists today. So our first session is going to be on renewable energy systems and storage. Moderator today for us is going to be Anson Sando from the IIT Madras Research Park. Anson is manager for energy programs at the Research Park. He focuses specifically on renewable energy, electric mobility, and energy storage. Anson's got work experience in the Bay Area. He's worked on collaboration space of smart infrastructure and holds an MBA from the University of San Francisco. Anson, may I request you to please call on all our panelists.
I'd like to first start off by just introducing our panelists for today's discussion by calling them on stage. First up, we have Professor Ashok Jhunjhunwala, President and founder of IIT Madras Research Park. Professor, please come on board. Next up, we have Dr. Ashok Krishna. Please do join us. We have Mr. Max Narasimhan, CEO of Play Solar. And we have 2 virtual panelists for today's discussion. Dr. Ganesh Das, Chief Strategic Officer, Tata Power. And finally, Professor Kothandaraman from IIT Madras. So great. Very good evening to all of us who've joined live from the IIT Madras Research Park. And welcome to all our online joinees from across the country and probably even around the world. Today's topic will be renewable energy and energy storage systems. We have a set of power pack panelists with us today, and that includes both participation from industry as well as academia. And I'd like to start the session today by providing a few data points on renewable energy and the landscape globally as well as in the country today. I know most of the experts here are already familiar with some of these points, but just want to set some context on this front. The share of renewable energy globally has increased by 10 times in the last 15 years. More than 80% of new electricity capacity addition today is RE-based. In India, the story is a little brighter, with the share of renewable energy doubling in the last 5 years alone, solar in particular, by growing over tenfold in the last 5 years. Today, standing at 100 gigawatt of installed capacity, renewable energy is now over 25% country's installed capacity for electricity generation. But there's a little bit of hidden detail in that last point that I mentioned. And that's really the debate between gigawatt and the gigawatt hour. We'll be diving into some of these in our discussion today, but I'd like to start the discussion and open it up to our panel today by just throwing open the question of the renewable energy landscape in India and what does the future roadmap in India look like, especially given solar and wind are taking gold and silver for the most part. What does it take to sort of complement these sources? And what do those sources look like? So I'd like to open up the discussion to the panel. And if anyone wants to go first, please feel free.
I think you have to ask people to go first. Otherwise, everybody will keep looking at each other. And since you didn't ask, I will just sort of say, I don't know whether everyone knows. Today, solar in India costs 2 rupees per unit, 2 kilowatt hour. That's the cost today. Wind, closer to 2.50 paise per kilowatt hour. Coal, historic coal is around 2 rupee 50 paise. But if you take new coal, where you have to put various pollution control devices, if a new coal plant is more at 3 rupees 75 paise. So coal and wind and solar in India is already cheaper to generate. That's the first reality that we need to understand. The second is this myth about 25%. 25% is a capacity. Capacity is not energy. Now, remember that solar and wind is not produced 24 hours. It is produced only part of that time. Since it is produced only part of the time, you have to take what is called plant load factor or capacity utilization factor, and therefore you have to talk in terms of energy per year. In terms of energy, we are still 8 to 9%. So solar and wind is very low compared to the rest. And we really need to expand that. So this 100 gigawatt hour has no meaning. We need probably 1,000 gigawatt hour or more. We have to get there. That's what has to happen. Economics wise, there is no really problem. Is there a capacity problem? Can we have 1,000 gigawatt hour solar and wind in India? Yes. There is enough land. We have done some computation that even small fraction of Rajasthan desert can actually get us all that we need. So there is really no capacity problem. And then wind, we can go higher up in the wind. We can use coastal. So there is no limitation. India does not have a problem if it uses solar and wind. The third problem that I want to point out is that solar and wind is available whenever God wishes, when there is a sunshine and when there is a wind blowing. It is not 24/7. It is not controllable by human beings. Coal power plant, on the other hand, are controllable by human beings. You can increase, decrease the quantity anytime. So solar and wind, when you generate, and it has to be used instantly, immediately. If you can't use it, it has to be dumped, unless you can store. So storage becomes a very critical element in solar and wind, and storage is not inexpensive. For example, a lithium-ion battery storage probably will add, if you want, suppose you put only 10 gigawatt hour into that, or whatever quantity you put, it will add per unit 8 to 9 rupees. That's what, in Indian context, at Indian interest rates. Do not think of European and American interest rates. You have to take everything into account. This is the total cost, including the depreciation, interest, and everything. So that is on higher side. And that's where one has to do lot of work. One has to do all kinds of innovations to really bring down the cost. It is possible to bring it down. I think today you can get closer to 6 rupees, but not much less than that today. There are other storage, of course. Yesterday I talked about chilled water storage. That cost is much lower. And since much of our electricity is used in air conditioning, we can actually also use that. So I just thought that I'll add these as the initial figures before others take off. Please. Yes, sir.
Max, do you want to go?
We haven't heard you yesterday, so why don't you?
Sure. Yeah. Hi, Mukundan alias Max. So I think Professor Jhunjhunwala mentioned the viable options, right, with solar ramping up. So one thing to note here is, just take, if you look at viable distributed energy sources, right? We're not talking about centralized sources. We're making the coal power plants with remote transmission and distribution, transmission losses being 40%. It's unheard of anywhere else in the world. We have 40% transmission losses still after several years of operation, several decades of operation. So that way the distributed generation is starting to make more and more sense, where you generate at the point of use. And as Professor Jhunjhunwala rightly pointed out, if you have the right battery configuration, you can store the energy during the off-peak hours or when the solar is not available to kind of offset your consumption during those hours. So in terms of overall per unit capacity that can be produced from solar, it is higher than what Germany is, because that's, we are blessed with a lot more sun than Germany, right? Although they are at 40% renewable capacity now, their solar generation is actually far less compared to us. So we don't need to go to that high to get the peak solar generation up, right? That's one point, which means that the storage capacities and the costs have to ramp up much faster. And India is the right market to do it with the right set of initiatives. Right now, to accomplish that, we need to have a time of day tariff, which does not exist, right? The storage costs will have to be spread and amortized over many years. For that to happen, the time delta, the cost delta in terms of time has to happen. And that's a policy initiative that needs to happen, right? And of course, the push towards reduction in transmission costs and the solvency of the utilities, enough non-technical problems to solve, right? I would like to state that.
Great, thank you, Max. Dr. Ashok, do you want to sort of chip in with your experience in the oil and gas sector?
So I think you heard from me yesterday, the oil and gas perspective. I'm wearing a different hat today. I retired from Chevron and started a company, co-founder, to do precisely this, right? Go after the most difficult problem to solve, which is long duration energy storage. So we'll talk a lot more about that topic later on when we get to that point. What I want to do now is add to what Professor Jhunjhunwala and what Max has said. One is we definitely need storage. The longer, the better. Hours are not good enough. I think if you read Bill Gates' book on how to handle the climate disaster, prevent the climate disaster, he says a company that can do storage from season to season, right? Not hours, not days, not weeks, but months to months, right? If wind is only good for 4 months in a year in India, how do you store that energy for the remaining 8 months, right? He said that's the company that's going to win. So that's what we are trying to do, which I'll talk about later. But to Professor's point, the cost matters, right? So we talk in dollars and cents. And so I was in the Middle East a couple of weeks ago. In the UAE, they've got solar plants at 1 cent a kilowatt hour, right? So that's the 1 or 2 rupees a kilowatt hour, right? It's already there, right? So it's incredibly low, and wind is a little bit higher than that. So then the question is there any hope that you can get storage on a par with those kind of costs? And again, the professor is right. Lithium-ion batteries are probably 6, 7, 8 rupees per kilowatt hour. Our goal is 3 to 4, right? Can you get to 3 or 4 rupees per kilowatt hour? And that's the challenge. The second challenge is scalability, right? Even if lithium-ion batteries get there, you need gigawatts of storage. How do you do that, right? How do you get scale? And I think to Max's point, you got to be able to amortize over a 30-year period, right? It's a utility business, right? If you put the capital in, let's say you build $1 billion project to have a gigawatts of storage, you better be able to amortize it over kilowatt hours over 30 years, right? So those are the issues we have to grapple with. So I'll stop there. We'll come back to this topic later.
Thank you, Dr. Ashok. I think we want to go and get some of the points from our online panelists, Dr. Ganesh and Dr. Kothandaraman.
Yeah.
Dr. Ganesh.
Thank you, Anson, and good evening once again to everyone. The point which mentioned by Professor Jhunjhunwala, Max, and Dr. Ashok is very appropriate. And if you look at from the perspective of utility, which is our job is to reach out to the consumer at the last mile and provide electricity, despite the fact what kind of consumers they have, what sort of paying capacity they have. End of the day, we need to supply them reliable power. And how does the landscape change now, given the fact that renewable energy is going to be a very critical kind of a driver in the future? Now, the point which I agree with Professor Jhunjhunwala, wind and solar, these are the two available renewable energy, which is not affecting anyone in whatever manner. I give an example. If you talk about hydro projects, water is used for different applications. It is used for agriculture, it is used for drinking purpose, and it actually touches a lot of dimensions of the ecosystem. So managing and harvesting water will remain a challenge, especially for a country like India. We have a constant growth in population, changes in the lifestyle, improvement which is happening at different level, at the rural level, etc. But if you look at solar and wind, there exists a huge potential. The wind has a huge potential. Still, we have not really looked at the way the other parts of the world, like for instance, Denmark does it for energy islands, etc., for offshore wind, etc. So that is one part of the dimension. And when you look at the renewable energy penetration, it can happen at two levels. One is, of course, at a level when you large distribute and when you produce, generate at a very large level at a desert in Rajasthan or offshore wind, and then transmit it the way it is transmitted to the other parts of the country. The second part is you actually do a distributed generation, the point which Max has been mentioning. So we looked at both the dimension together. We have looked at the fact that how large agreements to the renewable power can help us to address our consumers' requirement. Also, how do we really bring in distributed energy resources at the nodal level, at the distribution level? And both have a different strategy needs to be followed. For something which is generated miles away, obviously you have to get into large-scale power purchase agreement and do that. And when you are talking about the distributed energy resources at the distribution level, at the utility level, this is much more flexible, and it actually changes the ecosystem in a very different way. You have got regulations now coming in. You have got regulations coming in for the rooftop solar. Things are getting very attractive for that. You have got electric vehicle coming in a big way, and we have got also different ecosystem of IoT. The IoT, the edge of the grid, which is connected. You are having home automation solution. You are having demand response facilitated. We have the smart meter is coming in a big way. Smart meter is going to offer us a lot of data, information, and behavior pattern, wherein we are going to. It will be much more simpler for us to predict the supply for the demand from the consumer side, and then manage the supply in a better way. And I'm talking from an utility who has deployed technologies like the advanced distribution management system. We have an integrated GIS and many of such technology. How do we really are actually facing to this kind of a situation what we see now? We are having our strategy around having a rooftop solar and a distributed solar at different pockets. And then we are going to look at storage in a very strategic manner at the grid level, at the distribution transformer level, even at the pole level. And as you would all know, we have already installed India's first and South Asia's largest 10 megawatt grid connected battery energy storage system, which is based out of the lithium chemistry. We also have a 150 kilowatt storage at a distribution transformer level. And we are also deploying 10 kilowatt small storage at the pole level. And what this is going to help us is to address the requirement of different nodes, because nodes are congested. We have got challenge of space expansion. There is a challenge of capex expansion. And then the peak load is only for a small duration of time. How do you really address this challenge? That is what we are trying to look at. We have done some analysis to look at through the smart meter data, what are our potential hotspots, and how do we really address these hotspots through the combination of the distributed energy resources at our local nodal level, and then how do we really work around that? And maybe one point I would like to also mention is the experiment with lithium is quite an eye-opener, because lithium requires a lot of auxiliary consumption. For instance, if you are going to use lithium-based chemistry in a summer, about 10 to 15% consumption is for the auxiliary power for managing the AC and HVAC and all those things. And when you are looking at an alternate chemistry, for instance, if you are looking at a zinc-based chemistry or a vanadium-based flow battery, then the experience is different. So there is also a requirement to look at these chemistries as we are driving and forming our strategy for India. I'll stop here. Maybe as we move forward, some more points could be discussed. Thank you.
Sure. Thank you, Dr. Ganesh. I want to go quickly to Dr. Kothandaraman for his insights or thoughts on this topic. I know he's also working on organic materials in perovskite solar. As we look at that as the future and next steps for solar, I want to hear his thoughts on what they might look like going forward in the future.
Yeah, thank you, Anson. Good evening to all. I kind of sync with all the members here. There is no doubt we need to build several hundred gigawatt hours of capacity of energy storage. But you mentioned about the photovoltaics. I mean, photovoltaic is what we are doing is only for research that we are working on. Perovskite is a lot happening, but it is still not commercial worthy. The kind of price that you are talking about with the silicon is much smaller compared to energy storage. Can you hear me, all of you?
Yes,
Go ahead. partly getting broken. So finish that quickly.
Can yeah. I saw the screen was frozen. So yeah. So actually, my point is regarding lithium. Probably that may not be sustainable for long term. For example, the recent story of OPEC countries, what they do during lockdown, they bring down the production of petroleum products, and now they are not raising to that pre-COVID level. So they kind of restrict the production rate, so artificially raising the price. Same would happen with lithium also. We don't know when we are out to produce, build such big systems and we suddenly see a lithium shortage. That could be an issue. So the alternate, there are many alternative options already. The technologies are fairly matured, like sodium ion battery or sodium sulfur type of batteries, because the sodium cost is only about $0.2 per kg kind of thing, and it's available everywhere. So the other option is use of iron or some organic based redox materials. So if we build our energy storage system out of these materials, okay, probably that will give us energy security rather than depending on material flow batteries. We work on that. It's an interesting system in terms of performance is very good, but again, the vanadium you need to import. There is a lot of issues with that as well. So I have done a back of envelope calculation. Yesterday also I shared this. At present, we have about 700 gigawatt of energy generation capacity. Suppose even if I'm interested to store 20% of that for 5 hours, that amounts to about 700 gigawatt hour. So if I have a battery which is like 100 watt hour per kg kind of a specification, that amounts to 7 million metric tons of battery. And this is only going to go up. So imagine the entire world if you are going to electrify using the renewable energy, something like 16,000 gigawatt is what the generation capacity should be, even at present 2020. So the 20% of that is like 160 million metric tons. So that means that much of lithium may not be there. So we may have to depend on something very abundant, accessible to India when it comes to India, about our energy security. So that is why we are looking more closely on this organic and sodium ion based systems in our group. Yeah, I will leave it there. Yeah.
So I will like to say one thing. This is not, the whole renewable is not future. Renewable is today and tomorrow and day after. Therefore, whatever we talk about, we should talk in terms of not just technology, but also economics of it. We like to see the economics. Otherwise, we can talk this, that, what is available, what cost, how will it add today, how will it add tomorrow, how will it add day after. That's the point number one. Point number two that I want to make, which has not yet been covered. As was pointed out, we have done well in centralized solar generation and wind generation. We have done reasonably well in decentralized, where big rooftops are available, like half a megawatt hour or a megawatt or even 200 kilowatt hour. But we haven't done well when it comes to 10 kilowatt hour. Most of our small and medium sized homes, solar is not viable. Solar, battery, there are very few systems, and that is something that we really need to pay attention to. If you see MNRE's program of overall solar is doing very well. Their program for small and medium size, decentralized, is totally failing. That is something that, and yesterday Vijay Raghavan was also talking about, we have to look at DC if you want that to take off. And that's the second point that I want to make in this. I have some other point, but I'll pass it on.
Sure. Yeah, on the cost economics, which is very, very critical part, right? So on the storage side, as others have pointed out, lithium can get to roughly about $100 per kilowatt hour, right? That's the current target. But there are other battery sources. Take, for example, iron air battery, right, which is now getting very popular because they can get to 3 to 4 day kind of backups. ArcelorMittal just invested a huge amount of sum of money into that, yeah, to forming that.
What is the cost target? And when is
Cost
it
target is
likely to be available?
$10 per kilowatt hour.
When is it going to be available?
It is going to be available in 2 years from now.
Well, let's get them.
Pilots within a year.
Let's get even a pilot. Even a
Yeah.
pilot has not happened. I think numbers I've been hearing for years, I've not seen those pilots.
So let me, so I know quite a bit about this subject because all I've been doing is long-term storage. So this guy called Matteo used to be the head of stationary solar for Tesla in my neck of the woods in Fremont. In 2016, he quit because that part of Tesla wasn't growing as much as some of the other parts. In 2017, he decided to jump into this business. He went stealth for 4 years, right? So just 2 months, 3 months ago, he announced a $200 million fundraise for this company called Form Energy, and ArcelorMittal put a lot of the money in. So he would never say what the heck he was doing, except there was a metal air battery. So now he comes out and says, well, it's an iron air battery. And iron air batteries are done by NASA in the 70s, right? So he's working with a professor, Dr. Chang in MIT. They've got a better system. When I look at it, it still looks like a reversible rusting process, right? It's really the same old thing, right? So he says, well, it was there before, but we've got a new look at it, which is fine. But they're going to build their first demonstration plant of any scale, start it up end of 23, which usually means it'll slip a year or two, right? It always does. And so at that point, they are claiming 100 hours of storage, right? Now, if they can do it, they can do it for $10 per kilowatt hour, 100 hours of storage, and they are modular and they can be scaled, reasonably scaled. I think that's great. But there's a way to go, as Professor Jhunjhunwala said.
Great. I think those are all very interesting points. But before we jump into a deep dive on storage, I'd still like to hover around the generation piece for at least a few more minutes. Firstly, I'd like the point around distributed energy generation, especially solar, not taking off in India. And maybe, Dr. Ganesh, you have some thoughts around why it hasn't taken off and what we could do to incentivize the push towards distributed solar, especially in the homes and small, medium-sized enterprise front.
So, we have been grappling with this consumer participation and solar and investment in the distribution side in a big way. And if you really look at the state of affairs when it comes to the power distribution, still a lot of challenges are faced by the distribution companies. There are challenges that the tariff does not increase. There is a loss level, which of course you have talked about, but it is not a transmission loss. It is a aggregate technical and commercial loss, wherein the commercial loss plays a much larger role than the technical loss in there. For instance, in our kind of network, we are close to about 7.2 percentage ATMC losses, out of which the technical loss would be somewhere about 4%, and the commercial loss would be something like 3% at the distribution level here. So, and then the tariff, it doesn't get rationalized by the tariff. The tariff does not increase at all. When you are talking about the investment in the network, and for instance, for the first time, I don't mind saying this, for the first time, we have started looking at not to invest more in the capex, but more to shift more into the operational cost, because in any case, the tariff is not going to increase. So the challenge continues, different kind of challenge happens at the distribution level. While saying this, how do we really make this happen? So we have tried to look at that. How do we really get consumer to participate more? Is there some way that we can get some behind the meter, business models wherein the consumers start owning a rooftop, and then start, there are certain policies can come in, peer-to-peer trading can come in a big way. So how do we really get the consumer to play their role and possibly get the consumer to invest in the entire value chain of distributing energy, and then make it happen? So we need to have innovative business model wherein the distribution companies do not continue to bleed or invest, or either it gets application to that. And then another interesting point which Max had made is the time of use. Now, India does not have a very good, strong, encouraging time of use tariff. We really don't look at the peak, off-peak, the congestion in the network, the challenges we have around that. It is still to come. And if you typically look at some of the markets in USA, for instance, Texas, you see a huge difference between the peak and the off-peak. And peak and the off-peak is also going to drive a lot of things it is going to make storage a good business case. It's going to make electric vehicle coming in as a strong business case. And what I always believe is, if you typically look at storage and if you look at electric vehicle or storage around that, it is going to be a stacked up application. You are not going to get benefit out of one application, and you have to stack different small application to make it work. And I always believe that the second use of battery, when the electric vehicle is going to discard the battery, the second use of battery, how do we really salvage this battery into a stationary application is going to be the key. And a combination of the electric vehicle and the stationary application at the grid level is possibly going to make this storage work. I'll stop here, please. Thank you.
Sure. Thank you, Dr. Ganesh. Before we sort of jump into storage, one other question. It's very clear from the panelists and all of our discussions that solar and wind is taking all of the limelight. Should we even consider a third or fourth source, or should we just go ahead and build out large quantities of solar and wind? I'd like to get some thoughts on that around could there or should there be a third or fourth source for generation in India?
No, absolutely. I think the third or fourth source that's hidden, that everybody can play a role, is in cutting consumption, right? Energy efficiency project. It's not very sexy, but it is clearly an opportunity where, the DC aspects that Dr. Jhunjhunwala mentioned, where efficiency can be increased significantly, or, basic consumption methodologies using heat pumps rather than, water heaters to heat stuff. So many areas, the chiller approach, right? I think it's the non-sexy part, but it has to be done in a big scale, for which financing, energy efficiency financing has to come in a big way. And that is what will trigger the consumption. There's no point in ramping up generation through the roof or not, or on the ground, when your consumption is not optimized. So optimize that first before you ramp up, renewable energy generation.
I want to add to it. This afternoon, I had a company visiting us. They have a data center in India, in Chennai. They consume 20 megawatt hour of electricity. Their primary usage is in cooling. They so far have been using chilled water cooling, which gives you some decent efficiency. They are saying they have decided to switch over to air cooling, which is 40% less efficient than water cooling. Why? Because water is not available. They told us they consume where is the water consumed? In the chilled water. When you actually take the hot water and run it through the to cool the water using the cooling tower, they lose 6 liters of water every ton, and they are doing 6,000 tons. So they are using 36,000. 6,000, 6 into 36, they are doing 6 liters per ton, and they are using 6,000 tons. So 36,000 liters they are consuming every hour. And they say in Chennai there is not enough water. Yeah. Now, in fact, an interesting question is there a better way other than cooling tower so that they don't lose all that much?
Yeah, I was just going to add, Professor Jhunjhunwala, that we're also working with Intel to supply our technology to data centers. You'd be surprised. Most of the world's data centers use air. They have something called a Kyoto wheel, right? It sits there and sucks the air through the data center, right? And at best, they may have evaporative cooling, right? They spray some water in, right? So it is incredible to me, right? That the ductwork for all that, and it doesn't sound very efficient to me, but that's what they use. So it's an area where a lot could be done. Right, especially in the area of cooling. So.
Because there is not enough water, you can't afford to lose so much water. I checked with our own numbers. We are also losing water. Of course, we are using recycled water. But even then, what else can be done? Can the cooling tower be made differently? In fact, I asked my colleagues, can we trap the water vapor getting lost? I think simple problems we are not solving, and then we talk about very sophisticated technology. If all this will mean so much less efficient, I mean, energy efficiency is one of the key things. Yesterday, this room had a temperature of 21 degrees centigrade. And we're all sitting and shivering. That's the energy wastage. We can't talk about going green and continue to waste energy. I pulled up my team today and tried to figure out what went wrong. But things go wrong.
Very rightly said, Professor. Dr. Ganesh and Kothandaraman, would you like to add some thoughts on the energy efficiency piece especially?
Absolutely. I think, energy efficiency is something, because, we always say that when we can say, why produce, and then this has got a huge scope, and it is not something very difficult to do. And this has a opportunity from the behavior, very simple behavior, manual behavior, and then you also have now very cost-effective home automation solution wherein you can, control your temperature, because APIs are very open for any electronic items and all. So energy efficiency is of extreme importance. And what we are also doing is, when you're talking about energy efficiency, not only in the lights and bulb, but from the industry. And if you will be surprised the kind of inefficiency of the motors function in India. If you really look at we have done a huge, audit of this, and we have a startup company called Urja, and we have gone, and what they do is they look at they harvest they have a self-harvesting kind of a coil, and then they look at the energy consumption of the current and voltage, and we can calculate the efficiency at which each of the furnaces, each of the equipments are going, and it is huge. 2030. I'm talking about companies like Tata Motors and all, where we have installed and we have seen results. 10-15% is a straightaway saving which you do, and in larger companies, which is proprietor driven, and where you don't have so many equipments to monitor that, very huge. So industrial energy efficiency, especially when you are using a inductive load, is huge. You can make a huge saving on that. Lighting load and small automation, there is a huge opportunity for doing that. And then in the commercial establishments, simply by lowering 1 degree, 2 degrees centigrade for demand response can result into a huge saving. Compressor switching off and off for idling situation when you are identifying the non-critical load goes in a big way. We have recently done a pilot on the behavioral demand response by simply looking at a manual switching off on operation, which has given us huge saving. It is quite interesting to find that even domestic consumers can be a part of your demand response drive. Thank you.
Yeah, so what I feel is, as Professor pointed out, it's only 3 to 4% is a renewable energy generation at present. It's going to go up for sure. So if instead of instead of looking at storing that energy, we can bring in some behavioral change in the way these industries function. For example, instead of having regular way of slotting this, what do you call that, shift, you can have multiple shifts running parallelly when there is an energy available. So that means, because we have a lot of automation that is happening in the industry, so it can sense the energy availability, then automatically it switch over and start the business instead of doing the 24/7. They can have a parallel session and then consume that energy instead of storing. This is probably the way to manage, rather than putting the energy that is harvested into storage. Yeah.
So Ganesh, you have been talking about time of day metering. How do we get it introduced in India?
You see, as far as if you look at let me take an example of Delhi. Delhi, we have got peak and off peak. The difference is not by 20% minus plus. It goes like that. But what is very important is, if you look at the time of day tariff, we can relate it to one important political aspect. The tariff in India does not change primarily because one of the reason is there is a large domestic consumers who are consuming your electricity, and you are giving subsidy, and you don't want to block that port. And typically the industrial and the commercial customers pay very high. The time of use tariff, if we do some sort of a little more deeper dive into it, analyze that, how do we really make sure that the consolidated tariff or the average billing cost does not increase, but at the same time provide the TOU in such a fashion that the distribution companies do not get into loss. So one example is, for instance, you are looking at I'll give you one example which Tata Power BDL do. We buy a power purchase of average about 6 rupees 50 paisa, 6 rupees 60 paisa per unit is our average buying cost. And the average billing should be somewhere about 8.59, something like that. And if you typically want to look at an increase in the average billing, ABR as we call it, you have to look at time of use in a big way. At the same time, you will make sure that the tariff to the segment where you don't want to potentially want the price to go up, we don't touch that. So that is one important thing to look at. And also relating to the point which made on the shifts, there is a possibility to look at the time of use tariff and also can potentially encourage different shift pattern or different manufacturing pattern. The time of use is accepted at the regulatory side. There are models, but we have to actually work a little bit more to get them to see what sort of a right algorithm will make so that the tariff also does not get affected too much. At the same time, the losses also does not actually fall into the distribution side. And then we end up saving energy also while we do that, so that the peak, the objective of maintaining a straight line is achieved.
Great. I think it's very clear that managing the energy is also going to become a very important piece as we look to integrating larger shares of RE. But at this point, I think I'd like to address the elephant in the room that comes with energy storage. It's all very clear that storage is sort of the missing piece in the puzzle. But there are two separate problems to it. One is addressing the short-term duration of storage that's required, as well as the long duration storage that will be key to the seasonal requirement that Dr. Ashok mentioned. So maybe I'll first point this to Dr. Ashok Krishna. Do you want to sort of briefly touch upon the long duration storage and the technologies that might be addressing this gap?
Yeah, no, happy to do that. In fact, I'd like to start with the short duration, pick up on what Dr. Das said, right? So the US is all about peak shaving right now, right? As he said, there are a bunch of startups by IIT graduates, AutoGrid is one of them. And you can write all kinds of software to have that power shift, peak shaving shift. So in the US, in California, for example, if you can take power in the middle of the day and shift it to 4 to 9 p.m., 5 to 7 p.m., something like that, that's where the money is, right? So that's very efficiently done in the US, and batteries can do it. Flow batteries can even go up to 10 hours if you wanted to, right? So that, to me, that side of it is done. I think one important thing that Professor Jhunjhunwala said is that right now there is not a demand for 100 hours of storage. So one of our conundrums is you've got to keep your eye on the price, which is 100% renewable energy, right? You're never going to get there without long duration storage. Yet today, everybody talks about 4 to 6 hours, 8 hours, because that's the peak shaving demand, right? And so when you have a startup like ours, trying to keep an eye on the price, right, when no one wants it right now, right, and still be cost effective, right? That's what we're struggling with. So let me take 2 minutes to give you a quick primer on long duration, LDES, long duration energy storage. We already talked about the electrochemical means. Dr. Kothandaraman mentioned, the iron air battery. We talked about sodium sulfur, built a huge sodium sulfur battery in Abu Dhabi. It's got safety issues, not straightforward. So the battery side is clear, 4 hours for sure, possibly 6 hours, 8 hours, maybe even 10 hours if form is successful, right? So that's good. Thermal ones, Professor Jhunjhunwala has talked about, right? Cold water, hot water, that's known. Electrical, they talk about supercapacitors. I'm not going to go there today. You could talk about chemical, hydrogen, that may be the future, but that leaves you mechanical, right? So 2 mechanical ways to do it. One of them is called pumped hydro, which none of us is really that fond of. It's basically need a mountain, you need a lake at the bottom and a lake at the top of the mountain, and you pump the water up to the mountain when the electricity is cheap. And when it sits up there, when you need it, it could sit there forever. It's got a pretty nice round trip efficiency, 80%, because it just pumps. When you need it, you can bring it back. Unfortunately, most people don't have a mountain next to them or a lake or on either end of it. So Europe has put in about 500 megawatts of this and they're done, right? No one's going to do any more of that. So what's left, as Professor Jhunjhunwala said, is compressed air, right? Compressed air energy storage is very old. There's a plant in Germany that started up in 1978, still running. There's a plant in Alabama that started up in 1991, still running, right? Never duplicated. Why? Both those plants store about 100 megawatts of power. in a salt cavern, solution mine salt cavern. Two problems. One is you got to pretty much dig a hole, and you have to have lots of salt caverns that you can solution mine. India doesn't have very many of those. And then when you expand the air, you got to burn natural gas. In those days, they didn't care about burning natural gas. So they take the compression heat, throw it away, burn natural gas, and get half the energy from burning of natural gas. Therefore, it's not renewable, so nobody reproduced it. So a bunch of companies said, aha, I know how to store that compression heat to go up to 100 bar in 3 stages, put out a lot of heat. If you didn't do anything, the temperature would go up to 900 degrees, so I'll store that heat. Well, how do you store it? An aluminum bed and a hot water tank. That gets you about 10 hours. You can shift that at night when the sun doesn't shine. You bring that compressed air up and expand it, and you can use some of that heat. That only gets you so far. And we're not happy with that. Right? That doesn't get you all the way. So then the question is, where do you store this air if you don't want a salt cavern? There's a company in Israel and there's a company in China that's decided to build just lots of piping. Right? So I did the math on that. Yeah, you could probably store about 10 hours of compressed air in a pipe. You can have a bank of pipes. You can bury them shallow, like sewage pipes, like the Israelis do. The Chinese just go out in the middle of nowhere and build, miles and miles of pipe. But you're stuck. That's it, right? Even those pipes, if you have 10 hours of storage, when you come down to 5 hours, the power starts dropping off. That's no good. So we scratched our heads and said, how do we solve this problem? And we wanted to solve the problem for 100 days of storage, right? Not even 4 days. And so we came up with the idea of one innovation was, let's not deal with centrifugal compressors and expanders, which are hard to maintain, especially when the temperature and pressure goes up. So we use a water pump the water into a vessel. The water rises and compresses the air. You use a slipstream of water to cool the air and keep it isothermal, right? It's a water-based system. It's not particularly more cost-effective than the centrifugal compressors. Why we use water is if the sun doesn't shine, let's say I've used water, compressed the air, and I'll talk about storage in a minute, where we store it. You bring it back up, the sun doesn't shine for 10 days. What do? Nobody can do anything. The air is sitting there compressed at high pressure. How do you expand the air? You got to heat it up. Well, you don't have solar thermal. You don't have, the sun is not shining. Maybe you have industrial waste heat nearby, but you can't depend on that. We have a water-based system. So we can use ambient water at somewhat lower efficiency for those 10 or 15 days, who cares, and generate power. So that's why we stuck to a water-based system. Not that it's particularly cheaper, it's slightly cheaper, but it provides you the only way you can generate power when the sun doesn't shine or the wind doesn't blow, because you can use water to expand that air, right? Now, obviously, you need lots of water. It's a closed loop system, but you can do it. If you can heat up the water, the efficiency goes up, right? If you can't, your efficiencies, so normal compressed air efficiencies are about 65%. During those 10 days, you may be at 40%. Who cares, right? So that's one innovation. The other innovation, quickly, I'll wrap up, Anson, is we connected this to another big problem in the world, and that is abandoned oil wells. So oil and gas wells usually deplete, sometimes in 7 years, sometimes in 30 years. And then there are abandonment costs. So big companies like Chevron will spend hundreds of thousands of dollars to abandon each well, to clean it up, cement it off, pull out the tube. There's a bunch of work you have to do, right? The small guys just walk away. They don't do anything, right? So the state gets stuck with it. So there are 37,000 wells in California that are leaking methane that people have abandoned. There are $1 million a well, and they walked away from it. And the state is stuck with it. The California state wants to build 10,000 megawatts of storage by 2030. They've got 1,500 megawatts built so far, and they have nothing else. They came to us and said, we got nothing, right? Yes, farm energy, we'll wait and see. But how are we ever going to get to 10,000 megawatts by 2030? We need solutions. And can you guys take a bunch of money from us and build a demonstration plant? And we said, how much money are you talking about? 100 million? Would that do? I said, yes, we could do a 5 or 10 megawatt demonstration. And the idea is you probably want to avoid oil wells because it's very hard to get the pores out of depleted oil wells. They're always in the pores. And you're talking about introducing air, which is oxygen. So that's not a good idea. Gas reservoirs are easy because gas has been stored underground for 70 years, leak-proof. That we could do. But an even better idea in California is these deep wells have saline aquifers. You can pump the salt water out 5,000 feet above the leaking methane reservoir, seal it off, so you stop methane leak, You repurpose an abandoned oil reservoir that would otherwise cost money to abandon, right? You put the oil industry back to work, my yesterday's talk, doing something that's in the renewable energy, and they can make money doing that, right? And now, 5,000 feet above that plugged off layer, there are saline aquifers that you can pump the water out, turn the salt water into regular water with our technology and store the air there. And so that's what we're trying to do. We're trying to do a surface plant first, then we're going to de-risk the subsurface next year. In 2023, we expect to build our first 5 megawatt plant that connects the compressed air to underground storage. Why underground storage is in those wells in California, you can put 2 gigawatts of compressed air, easy, right? And think about all the abandoned wells all over the world, right? Now, I do have a map of India. Someone in the UK did a study on India. Fortunately, they primarily focused on North India. So they don't talk about the KG Basin, they don't talk about the Kaveri Delta. So we got to dig into it because it's really unknown in India, right? So that's the potential, is unlimited amounts of storage. It just sits there as long as it's leak-proof. You can have it for months on end and bring it out 4 months later. And basically the marginal cost of storage is zero because it's just the size of the reservoir, which is usually giant, right? So that's the goal we're after. And so we'll see what happens.
Very interesting, sir. Thank you for sharing your thoughts. I'd like to open it up to the rest of the panel. I know professors working on other kinds of technology solutions.
Yeah, I mean, this is something very much in the mind, particularly with respect to the wind. We have been looking at all kind of things, but one of the things that very early, but appears to be quite promising, is zinc air. Yesterday I talked about it, and maybe my colleagues will talk more about it. Yeah. So one of the things that I did talk yesterday briefly is for this wind energy being available for about 5 to 6 months in India, if you take all over North India and South India. And 5 to 6 months, it is there, but not as much. So we need part of that energy to be stored, not whole of it. And we are looking at zinc air as a potential. My colleagues, young colleagues are working on it. And we believe that it may turn out to be very cost effective. We still don't have the full numbers, but it appears promising. Basically, zinc gets consumed during the discharging. During charging, zinc is formed. And zinc has to be stored. This is something that, and similarly one can try aluminum air. I don't yet know about iron air as much, but maybe some of those things can be tried out. We need to look at, we are familiar with the work that you have been talking about, you have talked about it. Somehow we look at it as a far more complex work. Somebody else has to, at least IIT Madras cannot take a lead in something like that. With zinc air, aluminum air, maybe even iron air, we could possibly take the lead. Hydrogen is another thing. Partly, can I convert to hydrogen? Then again, the storage and all those issues will be there. Yesterday, briefly, it was talked about. But I think still we cannot give up on hydrogen. Hydrogen is, because the reason we cannot give up on hydrogen is because we don't know how to handle the cement industry and iron industry without hydrogen. That's the best option for hydrogen. So we are not even necessarily looking at hydrogen as a storage, but we are talking about whenever there you have excess electricity, generate hydrogen and then run these things.
Dr.Ganesh and Kothandaraman, do you want to chip in?
Yeah, I just would like to know what kind of environmental impact that would be if you use those abandoned oil wells for the compressed air storage. Would that be a problem in the event of earthquake or things like that?
Yeah, it's a good question, Mr. Kothandaraman. So in fact, we're trying to figure out who will give us.
Did he?
So I'll try and give you the answer, Mr. Kothandaraman, if you can hear me, right? The oil wells we're
Yes, sir.
talking about, we're not going to go anywhere near where the oil used to be, right? That's a fundamental axiom, is we're going to avoid the oil, cement it off, and up and down the length of the pipe, we're going to put sensors. So right now it's leaking methane, right? So we're going to stop the methane leak and put sensors up and down so that we are telling the state over the next 30 years that ever leaks, we'll shut down and look at it. Right now you got nothing, which is leaking, right? And as you know, methane is 30 times worse than CO2. Short-lived, but 30 times worse. So we have enough opportunity to do things without messing with oil reservoirs that, to your point, there are people in the US that purposefully introduce oil into the reservoir to crack open the shale rock and make it move. It can be done. Shell oil does it, right, as a way to improve enhanced oil recovery. It is done, but it does box you in. You have to avoid the flammability limits, corrosion limits, right? It can be done, but we're not going to go anywhere. We got plenty of other ways to store the compressed air.
Yeah, I would like to add, taking off bit from what you say, we have been exploring possibility of first a carbon dioxide pipeline. I think that is going to play a very important role because if you want to sequester the carbon dioxide produced in, let's say, cement plant, we may have to carry it somewhere else. And the best way is to use pipeline. Today, gas pipelines that are used for LPG, for various other gases, we could look at using those pipelines for carbon dioxide. And the other interesting thing that my colleagues pointed out, that if you are going to have a carbon dioxide pipeline, why not compressed carbon dioxide? Compress it. That's a storage. And then take it out. I think these are technologies that we should work on. But I want to repeat one thing. Yesterday, I had mentioned that there are 4 stages of any technology development. And very often, we at academia and academic debate get stuck to only one part, the R&D. That's important, very important first step, but equally important in the next 3 steps. You have to think of economics from day one. From day one, not after if you have done the R&D. It may be totally off. Your economics may be totally off, doesn't matter. But you will know where it is and what's the target. The second stage will be pilots, which will prove the beyond science, the technical deployment of that, as well as economics of it. Because till that time, the science cannot be used. And the third stage will be an early pilot, which can show the feasibility of deployment. And the final stage has to be large-scale deployment, which is really going to solve. And that's the time all these issues that Raman was raising will come. That is there enough lithium, or should we use sodium? I think we'll figure out. Tomorrow, solid-state batteries will come. I'm not worried about those kind of. The question is, what stage are we in? Are we in R&D stage? Are we in early pilot stage, late pilot stage, early deployment stage, and late deployment? I don't want to mix up this. My point is, whether it's a zinc air or it is iron air, it is in R&D stage. It is not even in R&D. It takes years after that to bring down the cost. It takes years after that to work out the safety aspect. It takes years after that to scale. You've seen this in lithium ion. And things change during that time. See what has happened over last year. And same thing is likely to happen in solid-state batteries and other batteries. But we must always figure out, don't talk across the stages. Don't talk about something being, see, sometimes the venture fund does invest in R&D and it wants to build a hype on top of it. It wants to build a hype as if it is in early commercial stage or late commercial stage. And there is a huge time lag. I haven't seen that time lag. Yes, it is getting compressed, but not very compressed. And I think that needs to be, we who are scientists, most of us are scientists out here, know that we must do R&D. But at the same time, keep looking at economics and keep on looking at how the things are going to evolve from their various stages. Thank you.
No? So for any problem, we need to look at exactly what the problem we are trying to solve, right? If you look at it, right, there's three ways to look at a problem. One is the philosophical look, and second is the technological look, and third is more a practical look. So if you look at all three ways of looking at that problem of climate change, right, that we are trying to avoid, the philosophical look is as follows, right? The number one problem that we are actually trying to solve is greed, human greed, right? I mean, that is really the problem, climate change. We have taken from our environment, from our future, everything that we want, and we want to continue to do that without compromising our comfort, right? So that is I mean, do we have at IIT Madras a department of greed? No, right? So we need a focused effort on how to minimize the greed. Is that through policy? Is that through actual effort in curtailing profits or making profits go for good causes? You know, Tata is doing a fantastic job of that. 66% of the company overall is owned by a foundation, right? They know they want to make profit in a good way. You know, I used to work for them, so I know that, and Ganesh can speak more about that. So that whole concept of greed is the real problem, right? You can put 10,000 technologists at it, but will we solve the problem of greed? And that's the philosophical look at it. The technological way to look at it is obviously we need to look at you know, the right technology for the right cost, right? So as Professor Jhunjhunwala pointed out, right, hydrogen. Let's look at it for in situ use in steel or you know cement plants. And don't bring it to the vehicles yet. When we're ready, we'll do it there. And like that, right now, for EVs, as EVs are ramping up, let's ensure that you have the ramped up energies coming from renewable sources. Don't start up another coal power plant to do EVs. We're just moving the point of pollution from one point to another. So practical way to look at it is, you know, do what is that cost right now where, you know, you can start scaling the right business from a practical.
Right. One more thing quickly. Sure. I just wanted to reflect on one thing Professor Jhunjhunwala said, the idea of thinking about costs right away. So about 2 years ago, I actually met him for the first time, pre-COVID. And the idea was, what if you don't have a subsurface storage? Could you do liquid air? So, you know, liquid air is 1/700th the volume of air. So you liquefy the air, you store it in cryogenic vessels, then you vaporize it and produce power when you need to. Very, very elegant solution. There's a lot of expertise in IIT Madras. Professor G. Venkatratnam wrote the book on mixed refrigerants. So we got all excited. We worked with him, Dr. Bhaskar. We were talking about building a demo plant in the Tayur campus. When we went back and did the work, the darn thing is 10 times more expensive. Okay. So the one company in the UK who does it, Highview Power, they have a cute name called Cryo Battery, right? Very nice, but it isn't fit for India. The cost is just too much. So we just gave that up, right? So that, I think what it says is you really have to think cost as early as you can and not say, let me do R&D for R&D's sake, and someday I'll meet the economics guy who's going to push me, right? You got to think right away. I think that point's well made.
Absolutely. I want to just, you know, throw in another point and maybe open it up to the panel for that. If we look at solar, and like some of our panelists have mentioned, we've seen mostly large scale or utility scale solar take off. Is storage going to sort of follow the same route? Or where is this storage going to be located? Is it going to be behind the meter at, you know, local campuses like the research park? Or, you know, are the utilities and the large scale storage systems going to sort of follow the same track as what solar is
following? Quick answer, our view, it's got to be with the utilities, right? There's just no way we can build this where the usage is, right? So where you have the solar plant is where you have to have the storage. You may not have our kind of storage, but whatever storage it is, and the utilities are not exactly, you know, jumping at the chance, right? They're not interested in 100 hours of storage yet. I think Dr. Das talked about the fact that peak shaving is really what it's all about. Ultimately, long-term, long-duration storage of very high capacity to enable 100% renewable grid, utilities have to play a big.
Does the utility panelists in the room want to shed some light on that?
Yeah, you want me to, you know, Anson, what I would like to, you know, put across the point is, if you look at generation of solar at the at a level where you are talking about generation at a remote place, and if you look at the constraints, now the PLF, the plant load factor is very less. You are producing to the maximum only at some point in time, and you have got a huge transmission lined up design to evacuate that peak. And most of the time, the transmission investment is standard when you are not producing it at the peak. I'm just trying to give a perspective on where do we really figure out when it comes to end of the day at what unit you are going to charge to the consumer. So this is a one big challenge what we have. And if you typically look at the application, we did speak about hydrogen, and we have been also trying to evaluate hydrogen as a source. And then the point which I made earlier when you're talking about electric vehicle and stationary storage coming in to create some sort of a feasibility for storage. And what I would like to look at is, if you're trying to look at hydrogen in a big way, we have to look at some sort of a symbiotic relationship. And I will try to probably look at two dimensions of the hydrogen application in the space of energy. If you look at hydrogen, there is a possibility to look at blending of hydrogen into the today's gas-fired plant. Is it possible to blend? And I've been told that 5%, 10% blending is possible with the present design. And then possibly you can increase it to the level of 30% of blending hydrogen to make it more, environment friendly. And then you have to make some tweaking into the generation, the equipment parts, etc. on that. That is one part of doing that. The second part which I'm talking about is how do you produce this hydrogen? You can actually produce this hydrogen by looking at, of using the solar generation or wind generation. And when you don't want to have a very big capacity transmission line, and suppose I design the transmission line in such a fashion that when I produce peak solar or peak wind, I don't necessarily transmit it, but I use it to, say, produce hydrogen. And hydrogen has got application not only from the utility point of view or from the energy point of view, but many industries also use hydrogen. Is it some way that we can possibly look at developing a symbiotic relationship, wherein you are trying to look at not only one industry, but different applications of a particular, hydrogen or maybe some other related things, and try to develop a use case around that. So I feel, as we are moving forward, of course, presently also we are looking at this problem, but when you're trying to develop a business case and looking at per unit cost of energy and looking at some of the produce which is going to take place in the other industry where the hydrogen and some of the related fuel is used, or some of the related the energy related value chain components are used. We have to look at it in totality, and that is where we really have to figure out a larger policy, which could either come at a national level or could possibly come at a level where there could be an industrial syndicate coming together to form this kind of a thing. It could possibly come out of a academic institution and a industry corporation also. So we have to look at all these things at a perspective, and end of the day, the fact is the per unit charge of electricity, what the consumer is willing to pay is the key part, or wherever we are not able to meet that cost, somebody is going to bleed or some subsidy is going to come in. Thank you.
Ganesh, I think you have got it right. The excess electricity at any point of time, for example, can be converted into hydrogen and then to ammonia. I mean, we will need green hydrogen and ammonia. Our complete agriculture depends on that.
Absolutely.
Will we get ammonia using that, or we use fossil fuel? And I think we have to move away from fossil fuel. That's excellent usage. And you produce ammonia during the time when you have excess wind. That we don't have to necessarily look at that other kind of storage.
Yeah, a couple of quick points on that.
And also the ammonia is much more easier to store and transport than hydrogen. And straight away you are addressing a problem, and also we have a very large application of ammonia here in India.
And also please remember that ammonia basically means converted into fertilizers, where you can have a distributed fertilizers plant. So that is possible.
I just want to make a quick point that I think Vikram's talking about this, that Germany does it now, right? When the power is cheap, solar power is the cheapest, they just split the water molecule and make hydrogen. Some is converted to ammonia, other uses. So that's clearly probably the best way to approach producing hydrogen from water. The other point that Dr. Das made is that IOC has announced HCNG. So they're able to put hydrogen into the CNG mix. Unfortunately, the way they do it is they take the CNG, put it through a steam methane reformer, and convert the methane into hydrogen to get about 16, 18% hydrogen in the mix. But in the process, they're producing CO2, right? So I'm not sure that's the best way to do it, but at least they're testing it out, right?
Can I add something here?
Sorry.
Yeah. I don't know you guys came across this. There is in Japan, this Chiyoda Corporation. This company works on storing hydrogen in the form of organic molecule. For example, they take toluene. Toluene is a benzene with a methyl group. It has got 3 unsaturation, right? So it can hold up to 6 hydrogen atoms in that molecule. So they reduce that, make methyl cyclohexane, and then they transport it in the ship to the industries wherever they need energy. There they will convert back into hydrogen and use it in the steel industries or whatever the industry they are successfully doing this between the 2 islands. That's called Brunei Darussalam and Kawasaki. So this, I don't know whether you come across, because they have about 20 megawatt solar panel there which produces hydrogen.
Yeah, Professor Kothandaraman, we know that very well. It's a company called Hydrogenius in Germany that's been doing it for 10 years. Chiyoda is doing it. And there are US companies that are beginning to look at it. Different types of molecules. But basically the idea is that you take a light aromatic, let it suck up the hydrogen at pretty low pressure, the hydrotreating catalyst, and then it's transportable. At the other end, you release the hydrogen. So it's a pretty simple technique.
Different thing, one point that I want to make. Our industry needs to take a little bit of lead. I mean, people like you, Ganesh, others, and put the exact challenge to scientists. Today, Indian scientists are capable of actually cracking the problem in a relatively short time. I want to once again, yesterday I talked about it, our young scientists that I see are far, far better than what we were. I mean, I see our young faculty members, and not just in IIT Madras, pretty much anywhere else. They're so good. But the point is, they need to be kind of little bit somebody has to point out, this is our challenge. And this is the cost challenge, this is the technology challenge, this is the science challenge, solve it. And I think this is what you briefly mentioned, Ganesh, Industry Academia, and I think Kothandaraman also mentioned that. And I think that needs to be really harnessed. And we are precisely trying to do that at the IIT Madras Research Park. Point the problems and we will solve them.
I'm just going to say, Prof. Jhunjhunwala, you just articulated the whole purpose for this Energy Summit, right? We dreamed up this summit to expose IIT Madras professors to the kinds of problems that are out there, so they get exposure to that, because we know they can solve them. They just need a pathway to what those are, right? So thank you for that, because that's as good an articulation of the summit as anybody could do.
Absolutely.
So I'd like to point out 3 areas where some exciting technology is happening. I don't know how many people are aware of it. One is on the furnace side, the age-old furnace. So using a technique called partial hydrogenation, right, where the fuel itself has some hydrogen in it, right? It can be firewood, but not fully treated by removing the moisture and adding the right kind of ventilation system inside the furnace, where you can simply, just by the mechanical process, improve the efficiency by 30% or more, up to 50% in some cases. And you can use municipal solid waste or even wet firewood. So this is a technology that we are trying to proliferate. Already 80 systems have been deployed. We're trying to get this to mass scale with the Coca-Colas and the others of the world who are using all kinds of furnaces. So this is one example. Right? The second space is going back to what Ganesh was saying on the technology side, where peer-to-peer energy trading. Right? It's going to take a while to happen in India, but it's already happening in the US in pockets, where this whole concept of microgrid, where containment of whatever is happening at the energy level will be within that microgrid, right? It could be megawatt scale, it could be even gigawatt scale. So at a micro level, it is still called, less than a megawatt, 500 kilowatt, that sort of range. But there are several applications using peer-to-peer energy trading using blockchain or something, some kind of a distributed ledger system. We are working with a couple of companies and also utilities in Malaysia, where we're doing some kind of peer-to-peer energy trading for REC credits, renewable energy credits, where you don't need a third-party certification, right? And it takes money and it saves a lot of cash for them. Second is distributed battery systems in an area where your consumption prices are varying, right? The peak versus off-peak is more than 50%. And it makes a lot of sense to go storage distributed rather than turning on your peaker power plants. You just turn on the batteries and you get the energy where you need it. And another application of blockchain-based peer-to-peer trading is the chiller application, where there's a hotel chain where the chiller is up there. The chiller guy comes and installs it and runs away, doesn't maintain it. Every time there's this 1 or 2% change in humidity, the entire Malaysia goes up in terms of their consumption, and there's nobody to maintain it, and they have to turn on the peaker power plant. So this can be done using a smart contract where working with a few specific vendors who will actually maintain it. If they don't maintain it, they get penalized. If they maintain it properly, they get incentivized. Business model innovation. That's all it is. And with the right technology at the right place.
Absolutely. I think it's clear that there's a requirement almost of smart approaches to addressing the same problem. And just on that note, I'd like to sort of shift the discussion a little bit on an approach or a solution that was proposed recently by the Prime Minister of India on building an international grid around the concept of one solar and one grid. Sort of want to open it up to the panel to sort of get your thoughts on whether this is feasible, what are the challenges that we face, and does this really make sense for the future of energy tomorrow?
If you stop fighting between nations, it certainly does make sense. I don't see any reason why a grid all the way from Australia to Europe can't be put. Today, high power DC transmission can easily be put. The losses are not going to be very large. We just have to get together. If we stop, if we don't, we make too much of our differences between human beings, one set of human being and another. If you stop doing that, I think this is a project is doable. Fairly, you can start from Australia, go all the way to Great Britain, and at least India comes somewhere in between. This problem is solved. 24 hours.
Yeah, I was going to say that everybody got excited about this undersea cable from Morocco to UK, right? So there's this concept of undersea cables connecting South America, India, and the Middle East. So in theory, it's very doable, right? It's got to be done through that kind of.
I remember when we started fiber optics.
Yeah, that's the example.
About 50 years back, 40 years back, 40 years back. It was a big challenge. People were saying, no, it's not going to happen. Yeah. Then when we took over Tata Communication, Tata Communication took over Flag. I was part of the board. And how we actually very quickly put it all around the world.
Yeah.
And then I don't think it's as big a challenge as it is. But, biggest challenge will be, will nations create problems for each other?
So we've covered the philosophical aspect and the technical aspect. Let me come to the practical aspect. Let's cut that 40% loss in our own transmission line before we start connecting other grids to it.
We have it
Very
in
rightly said.
transmission lines, the losses, or in distribution lines? I want you to tell me. I thought the most of the losses are in distribution lines, not in transmission lines. I thought transmission lines in India are also not very lossy.
The losses in the maximum losses is in the distribution, and the distribution would include not only the network, the losses during the transmission at the inside the distribution, but it is the commercial loss. So Max, when we are talking about losses, it is largely the commercial loss, which is there, and India measures it very nicely, called the aggregate technical and commercial loss, at where the technical component is very less.
What is the transmission loss now between Delhi and Chennai? Rough idea, if you were to throw a number. What will be the transmission loss between Delhi and Chennai? For not even a DC, let's say even the current AC, high voltage DC, AC.
I think it will not be more than 1.5, 2% because it is transmitted at a very high voltage.
Yeah, I think the technical or commercial loss is basically theft. Let's not flower coat it or whatever it is. It is what it is. So
Right.
we need to. At an international level, that scale is going to be much larger, and you have
No,
to.
no, Max, I have a point to what you're making. In US, the commercial losses will be much more than what is the loss in India. Because US does not measure it and capture it the way India does it. So US calculates T&D losses. They don't, nowhere in the world AT&C losses is spelled out the way India does it. I think there's a big difference there, and the utilities there are allowed to, whatever is the commercial loss comes in, they are allowed to just wipe it off. Where in India we don't do that because of obvious reason that the commercial losses were very high.
Now today with IoT and communications the way it is, there is absolutely no reason for this. And you want to, of course, provide low cost electricity to those who cannot afford it, but do direct subsidy. There is no reason. I think there is apparently a bill now in the parliament. I read your CEO's Praveer Vora's article in Economic Times a week back. I was hoping that Praveer will be here. Yesterday he was not there, and I do hope both you and Praveer come to IIT Madras Research Park sometime. But there is a bill. You just do direct subsidy to the people who cannot afford electricity. Don't hide it under commercial losses. And everybody else who can afford, let them pay.
Very true. And that sort of points me to one question that I want to ask. We're almost running out of time here. As to what is the role of the utility or the DISCOM in this era of renewable energy proliferating? What is the utility and DISCOM play? Because its traditional role is almost changing all the much as we sort of integrate more solar and wind in our resources.
So definitely what we feel is the participation of the consumer is going to come in a big way, and the behind the meter activity is going to increase. What we feel is, and then what we are also seeing is once this new Electricity Act gets modified, amended, or it comes in through, the network is going to be separated and the retail is going to be separated. And once this happens, you're going to see a lot of combinations and options available for the consumer to look at. And then, incidentally, we should not shy away from the fact that, and the point is very simple, the point which Dr. Jhunjhunwala mentioned about DC. Today, many of the applications many of the appliances operate by using DC. And we are eventually converting AC first, DC to AC, and then we do a conversion again back to DC for many of the appliances. I think somewhere, we need to look at that in a big way, and we have not put too much thought about it. And just to give an example, the same line which carries AC, and the moment you convert that into DC, the capacity increases drastically because of the fact that you are transmitting DC. But of course, there are certain safety norms which needs to be looked at. So the point I'm trying to make is distributed energy resources at the utility level. I'm specifically talking about that. And the rest which comes through to the utility comes through a purchase agreements and whatever transaction which happens in the marketplace. But the utility at the distributor level needs to play a big role. We need to look at some innovative way to look at the roofs. For instance, I know about a startup who is part of our incubation center. What they do is they just go and make an investment on a rooftop of somebody else. And then, they sell that as a concept. You can actually buy, even if you don't have a roof, but you can be a part of that, you can contribute to that roof, and then you can use it to subsequently trade. And that could be possible if you are having a, say, closed kind of a, set of apartments or a community. But actually these kind of practices to come into the fore, the regulator has to start looking at this with a positive mindset, and then possibly encourage the consumer participation in the big way. So two things, regulatory changes needs to happen because still a lot of things are regulated. The second part is more consumer empowerment and participation.
I would just add one thing from the California that we haven't touched on at all today to our discussion is what happens to the primary utilities like PG&E, Pacific Gas and Electric in our area, who are bankrupt anyway because of forest fires. So I come along, I've got rooftop solar, I generate 16, 17,000 kilowatts in a year, but I don't want to go off the grid just in case things don't work out. So I get to tap into their grid. So they built the grid. And so I'm not allowed to be islanded. I could buy a couple of Tesla batteries and be completely on my own, but they're not letting us do that because the poor guys who built the grid need to be compensated. So if you notice, our chief minister just wrote to the prime minister last week about that very point, right? So all that's got to come to terms as we move forward, I think. So anything you want to say about that particular issue, Max?
I mean, there's several things that are happening, right? So TN is the only state that has not ramped up in terms of the electricity tariff compared to the other states. So there's a push for that to happen, and due to political reasons, that's not happened for a while. Now they're forced to do that, and also, at the same time, they are pushing for utilization of their own electricity rather than going in a large way solar, even though RPO obligations are there. I mean, I'm personally aware of a 10 megawatt project which was commissioned, and a big delegate was there and went there and saw it and said, sorry, it cannot be approved because it will set a precedent for other guys doing captive. So this is
Right.
I have a
One final
question.
comment.
I have a different question. Those who are expert in solar, I know Kothandaraman is. Now that the cost of solar has fallen like anything, and the next generation, perovskite and all those things are also coming, which will make the cost fall even more. Can we think of flat rooftop solar instead of at angle? Today we deploy it at angle at which it gives us the maximum power. Can we think of flat rooftop? A rooftop, can we design a rooftop which will kind of also give us shade and not let water also fall in, so that it can be actually mounted about maybe 6 feet on the roof, so the roof can also be utilized. If that happens, and what Ganesh mentioned, that maybe all roofs can have solar and maybe electricity can be taken and then done, how much really the loss will be? Will it be 5-10%? And will the cost be such that today with the falling cost, it may not matter? So this is a totally off the cuff idea.
Go ahead, Max, but I want to
just
talk about Elon Musk.
I think-
So you go ahead.
Unfortunately, we're running out of time, so a quick
Very quick.
comment,
very
and then we
quickly,
can
go ahead.
close.
possible, and it doesn't have to be, it cannot be perfectly flat because you need the water runoff. So it can be 3 degrees or whatever, and there will be some performance loss, not more than 5% for a place like Chennai. But if the northern you go, the azimuth becomes larger. Let's say in Kashmir, you need to be at 35 degrees tilt, and if you're at 0 degree tilt or 3 degrees tilt, the loss will be 20%. So that kind of losses can be taken care of. But the raised roof platform is already happening in a big way in cities like Bangalore, where everybody wants to use their roof. And I see that already being done here at IIT Madras.
So just very
Except
quickly, I
that it
wanted
was
to-
still at angle. Doing
Yeah.
it flat will really help.
Yeah, just a quick word on that is that Elon Musk started a company 5-7 years ago, and the whole idea is make the roofing material solar, right?
Yeah.
So it doesn't matter if it's flat or whatever it is, the entire roof is solar material, right? Now he's struggling financially with that, right? It hasn't taken off, but that's the concept. So
Great. I think it's been a very stimulating conversation, and we'd love to sort of carry this over to dinner. But I'd like to close the panel by putting a little bit, putting everyone a little bit on the spot by asking each one of the panelists for your prediction on when we will actually hit net zero in India. So timelines on when we will hit net zero in India. Dr. Ashok, do you want to go first?
Want me to
Anyone wants to
start?
take?
Let
Well,
me go.
yeah,
I
go
mean-
ahead, Dr.
We will make it by 2050.
Okay. Max,
Yeah, net zero emissions, I suppose
Yes.
that's what I
yes,
just want to
net zero
clarify.
emission.
Right, so yeah, I think 2040 is possible, but with the right set of technologies matched with the right business models.
Yeah, who am I to second guess the prime minister? 2070.
Going the diplomatic route. Dr. Ganesh and Kothandaraman, final words.
Yeah, in fact, of course, this is a country target, and we have been following this quite a lot. And then Tata Power had made a net zero target of 2050, and we have revised it to 2047. So we feel that at least from what we need to do, we will do, and country has to do its bit. But certainly, we will be facilitating this as we move forward.
I think 2047 is a great target, 100 years from independence.
Yeah, I agree.
Absolutely. Yeah, I did mention country. Kothandaraman, you want to?
Yeah,
Sort
I resonate with them. Yeah, I too believe the same way.
Absolutely.
2040.
Great, I think that's a perfect note to end this
I think
discussion.
this energy forum adopts 2047.
Thank you so much. And I think that's a perfect note to end the discussion. I hope we can carry this over at dinner. But thank you all once again for joining us, and thank you to the panelists for your beautiful insights.